Oh, we are so super close to being done. This is probably my favorite lecture in the whole class of Calculus 1. We're going to talk about section 5.7 in our book on substitution. And in this section, the major outcome is that I want you to be able to undo the chain rule by using the method of integration by substitution. Some people call it u-substitution or just plain u-sub. There's an obvious typo here. I'll just go ahead and draw attention to that. There's only so many times one can type the word substitution before it really stops making sense. I would like to draw your attention to the set of whiteboard videos that I have on this. If you're struggling with this content at all, I would like to invite you to take a look at any of those videos. In particular, I made this one right here as just like a genuine, like, here's some help. Where I play with techniques for identifying what you should be. I'm going to move through the examples in this video pretty quickly, assuming that you're following me, because you can always go back a few seconds and pick it back up or ask in class, and because I have these videos here in this other format. So what we're doing is we're building on the chain rule, and we happen to know that the chain rule, or what I was calling composition rule, is for how we take derivatives of compositions of functions. So remember that the chain rule said that the derivative of a composition, right? So I've got an inside function right here, says that I need to take the derivative of the inside right there and multiply by its derivative on the outside. So it remained fixed on the inside, and then its derivative popped up on the outside. So the derivative of f of g is the derivative of g times the derivative of f, but we still have this composition on the inside. Now, because integration undoes differentiation, I should be able to slap an integral and a dx around both of those and get equality. And it's true. It's true that this does work. And this is exactly what u-substitution is used for. U-substitution is our technique for doing this. So there's a technique for undoing the chain rule, and it's essentially we want to rewrite as this. And so we will start with this. And our major goal is to figure out, what is this? Okay, so that's the major goal, is to figure out what's g supposed to be. So here it's called g, and maybe it would have been better if earlier in the class we called it u, because essentially if I just take my g's and because it doesn't matter what that thing is called. So if I replace those with, that's way too thick, with a u, then you have exactly u-substitution, right? So that's where the u is. And I don't know why they use u and not g, but that's what they do. Okay, so a short, quick summary of u-substitution is that the integral of this composition, the derivative of this composition of functions, is equal to the derivative of this right here. That's application of the chain rule. And then this right here, well, if I have something prime and then I integrate it, I get the thing without a prime after I'm done integrating, plus some constant c, because the derivative of a constant is 0. So the method of substitution then says some hypotheses right here. This is a theorem. It's the worst spelling of the word theorem ever. Whatever. So if f prime is equal to f, so I have a derivative antiderivative pair. All that really says is that this right here just says f is an antiderivative of lowercase f. That's all that says. And I have u, a differentiable function whose range includes the domain of f. That's just a restriction necessary so that we don't accidentally include infinite discontinuities or points where functions are not defined or something like that. Then I have this statement right here, which is exactly what I wrote on the previous slide. So the integral of f of u prime, is equal to capital F of u of x plus c. And a way of seeing that is because I would have capital F prime, because capital F prime is the same as little f, right? So It's just the chain rule. That's it. I would recommend you watch my 2 first Lightboard videos that I had on the first page at this point. I linked one of them here because I think that's probably the one that's probably more pertinent. But I do go over these steps in that same video, in my video 1. So in video 1, integration by substitution, and this is a link, so if you have the PDF on your computer, you can just click that. That's why it's in a box like that. It's a link, and it'll take you there. Okay, so here's the steps, generally speaking, that we're going to use for substitution. The first thing that we're going to do is figure out that we need to use substitution, because unless you have a hint that you're going to want to use substitution, then how are you going to know to use substitution? Well, there are lots of functions that can't be integrated using substitution, for which some other method is more appropriate. And so the step 1, look at the integrand for a piece. That's a multiple of the derivative of another piece, is really identify that substitution is an option here. And then I say try a u. Right? What we're going to do is we're going to let u of x be equal to the inside piece. And we'll get some examples down below here. Again, if you watch this video, you'll know exactly what I'm talking about. We need to take the derivative of u and get du. And we'll have some practice on that down below. Find du in the integral, multiply it by a constant if it's needed, and substitute. So then that transforms. And now the integral should be simpler at this point. And then we'll rewrite and attempt to integrate. And if we fail, then go to step 1 and start over, because maybe you need to try a different u, or maybe you need to try a different method. Maybe you need to do integration by parts, or maybe there is no antiderivative, the formula for the antiderivative, and you can only do it numerically. There is an infinite number of those functions. I will explicitly note that this is a skill that you master through repetition. If you look at the problems in the book for this section, there are so many problems for this. Not even getting to the challenge problems, there's 107 problems in the book, right? And so what that says is that there's a wide variety of these things. They look different, but you can get good at it by practicing. So if you just do 3 of these, I don't think that you should believe that you know how to do it. If you do 30 of these, I think you're on the right track. I did not assign 30. I did assign many. Okay. So let's start with an example. And so I want to look at this function right here, and I'll focus on it at higher up at first. Step 1, though, says look at the integrand for a piece that's a multiple of the derivative of another piece. Okay, so I'm cruising here, and I'm like, oh, 3x squared, that's the derivative of x cubed. Oh, cool. That part right there is x cubed prime. That's exactly what I want. So this integral is the same as x cubed prime times sine of x cubed dx. And that's exactly the situation that we want. I probably will never again write something like this because it's not useful. Instead, we're going to do the method of u-substitution. And so I'm going to let u be the thing that's inside of there. So we'll let u x be equal to x cubed. And now what we need to do is we need to be able to substitute away everything in the integral, including the dx. So I'm going to write that du dx equals 3x squared. And then I'm going to do this thing that looks like an abusive notation. I'm going to move that over there. So I'll have du equals 3x squared dx. And there is some pretty cool mathematics going on here. When I write this statement, this thing right here is essentially the determinant of a Jacobian matrix for a transformation. So we're transforming from x space to u space. And this right here says how space scales. Okay, so now we want to identify where in the problem is this, and then everything inside of this expression right here should turn into something having to do with u, and there should be no x's left over. So goal. No x's left over. So I have the integral of 3x squared sine x cubed dx. This part right here That's our friend du. That x cubed right there is u. So this is equal to the integral of sine of u du. So much easier. I totally know how to integrate this thing. Well, that's equal to minus cosine of u plus some constant c, and then u is just equal to x cubed. So I have minus cosine of x cubed plus c. And so that's what our antiderivative is. So the integral of 3x squared sine of x cubed dx is equal to minus cosine x cubed plus c. And so all we did was undo the chain rule. We can check our work, right? Because we can take the derivative of this thing. Right? So if I do that, and I take the derivative of it, minus cosine goes to sine. I need to chain out. And then the derivative of c is 0. And that's exactly what I got. What I got there is exactly the same as what I started with. So those two things match. That's the big check mark that we were looking for. Okay. Let's play that game a couple more times. So let's evaluate the integral of x times x squared plus 9 to the 5th. Our goal is to find a piece that's the derivative of another piece. I said multiple of. So I want you to look at this and find out what's the relationship. If I take the derivative of this, I'm going to get 2x. And I see this is 2 times x, right? Sorry, that's a half times 2x. There we go. Let me go ahead and write that down in permanent. So if I take the derivative, and then this part right here is the half of 2 times x. I don't want that center dot. Right? So that's exactly what we're going to do. We're going to say let u, because this is a creative process, that let right there says that we're making a decision. So then du is equal to 2x. So you can always like kind of skip this like multiplication by dx step. And so from u equals x squared plus 9, I can just go du equals 2x times dx, right? This thing right here is just the derivative of u with respect to x. Okay, so and then just like tack on a dx to that end of it, because like there's no sense in like doing that step every time. So now I want to try to find a multiple of this. Sometimes you'll be able to do it, sometimes you won't. If you won't, then u-substitution wasn't the right thing, or maybe you chose the wrong thing to be u. There are a number of good problems in the book that illustrate choice. So I see x, oops, I didn't mean to include that, to the 5th. Right there. But I'm missing a 2, so let me rewrite this. So I need a 2 right here, but I can't just multiply by 2, but I can multiply by 1. It's one of the oldest tricks in the book. So now this part right here, that's our friend du, and we had to multiply by this 1 to get it to happen. So that's pretty common. You got to get good at that. And then the stuff inside of here, that's u. So this is equal to a half of the integral of u to the 5th du, which is equal to a half of u to the 6th over 6 plus c, which is equal to 1 over 12 of x squared plus 9 to the 6th plus c. And if you want, you can differentiate this and check whether we get the same thing back or not. And we will. Let's do another one. I like this problem quite a lot. It's got a fraction with these negative powers. I find that students often need help with the negative powers right here. I'm not going to rewrite it in terms of a negative power yet. I'm first going to check and see whether I can do something with having to do a u here. So look at this. I've got a 3 and a 2. I've got a 2 and a 1. I've got a constant and nothing. So things seem like they're lining up for me here. So I think we should try u equals x cubed plus 3x squared plus 12. And then du is equal to 3x squared plus 6x plus 0 dx. So du is equal to 3 times x squared plus 2x dx. And that's what I need, right? So like I want to see the whole thing over here inside of here. And so I'm going to multiply by a 3 and a third. Another perspective on doing that, if you don't like that perspective, is I could take that 3 and I could move it over here. And now when I do the substitution, this part right here is going to become du over 3, and then I'm going to pull that third out front. But I don't like that perspective as much. And so I'm going to elect to not do that. So again, I'm going to put a 3, some parens, and a third, because that makes more sense to me. I like multiplying by 1. So let's rewrite this expression then, that this is equal to a third of the integral of, let's see here, this whole thing right here, du. Great. 1 over, and the thing inside here is u. Now I'm going to go ahead and do that minus sign deal and integrate. And then I've got to put in what my u was. X cubed plus 3x squared plus 12. Why did I write 16? Okay. Not that bad. It's really not that bad. I want to go on like a little sidetrack here and be like, well, what if we had integral of x squared plus x over x cubed plus 3x squared plus 12 dx. So again, looking at this at a cursory level, I've got a 3, I've got a 2. Those are off by 1 from each other. I've got a 2, I've got a 1. Those are off by 1 from each other. Great, in the right direction. Great. I've got a 0 and nothing. All right, so things are like matching up. And so then I'm going to be like, well, okay, let's try letting u be that. All right, same exact thing as last time. du equals 3 times x squared plus 2x dx, and it's like, oh, like I can get the 3 there, but like I can't just get another x. So we fail. Aw, we failed, but that's okay, because failure is inevitable. You will fail things. Like, things are going to be hard. You'll make mistakes. Like, things aren't always going to work out. And, like, as far as integrals go, there's no value attached to failing to integrate this function. This function probably doesn't have a symbolic antiderivative. Probably doesn't. And that sucks. I guess. I don't know. It doesn't suck. There's no value to it. It just is. If it sucked that there was no symbolic antiderivative, then normal distributions would suck, because the cumulative density function for... no, I'm not going on that sidetrack. Take a course in statistics. It's great. Okay. So I wanted to repeat the same calculation, more or less, because I think there's utility in saying the same thing a few times, but stuff that's slightly different. So initially, we started with stuff that was to the 6, and then in this one I was like, well, let's change a coefficient, and in this one I was like, there's no to the 6. Right? It's just straight up. So we'll see what's different about this one. We're going to play the exact same game with u. Hopefully this is becoming familiar. U equals, I'm going to do it to be the thing in the bottom, the thing that's the other thing is the derivative of x cubed plus 3x squared plus 12. Fine, we've done that several times now. Du equals 3 times x squared plus 2x dx. All right. I hope this is starting to feel familiar. We need a 3 right here. I need a third right there. Great. So when I rewrite this whole thing here is u. This whole thing here is du. So this is equal to a third of the integral of 1 over u du. And remember, the power rule doesn't cover the u to the minus 1 case, which is this. So this is a third of the natural log of the absolute value of u plus c. I need you to memorize that one. 1/3, the natural log of the absolute value of x cubed plus 3x squared plus 12 plus c. Really different, right? Really different. So whether you've got powers in the bottom or not makes a big difference, right? If that's a 1 right there, then it turns into natural log. But when it was a 6, it goes to minus 5. Alrighty, let's do a few more. I want to do some of these ones like this. You'll see these a lot in physics classes, so you need to be able to do these really easily. Again, we're going to let u be the thing that's inside. Seven theta plus 5. Du is equal to 7 d theta. I don't have a 7, but that's okay. I can get one for free. And now we'll group them together. Du integral sine of u du. 1 over 7 times minus cosine of u plus some constant c minus a 7th of cosine of 7 theta plus 5 plus some constant c. Not that bad. Let's keep plugging along here. This one's really super similar. This one and the one above it, it's so common. They're so common because like, oh, that number's there and that number's there. That's what happens. So when I look at this problem here, I know immediately because I have experience, and I want you to have that experience too because you've done lots of problems, that this is e to the minus 9t over minus 9 plus some constant c. Like, I don't even need to do the substitution. I know what happens. Because when I differentiate this thing, this minus 9 is going to come down front because of the chain rule and cancel with this minus 9, and I've got e to the minus t left over. Okay? Let's go ahead and do it step by step. So I need, my friend, a minus 9. So that's equal to minus 1 over 9 times the integral of e to the u du equals minus 1 over 9 e to the u plus some constant c equals minus 1 over 9, 1 over 9, Ciliana, 1 over 9 e to the minus 9t plus some constant c. One more I want to do with you here. This one's a little bit surprising. Now, I don't know of any function off the top of my head whose derivative is tangent. Because, like, all the ways to get tangent out of the basic trig functions were, like, secant tangent or secant squared, and I don't have either of those. So as far as getting off the ground on this problem here, I think the right thing to do is to rewrite this as the integral of sine of theta over cosine of theta d theta. And now there are multiple ways to go, and if you just start doing this problem, like say you pause it and try letting u equals one of those two parts right there, it'll probably work out. I'm going to go ahead and let u be the thing in the bottom here. So then du is equal to minus sine of theta d theta. Typical multiplied by 1. So that's equal to minus the integral of du over u. And I hope you're getting more familiar with that. If you're not down with that, that's minus the integral of 1 over u du, which is equal to minus the natural log of the absolute value of u plus some constant c equals minus natural log of the absolute value of cosine of u plus some constant c. Yay! If I'm going fast, it's because I'm well practiced. If I'm going fast, it's also because I know my videos get long and I know you can just watch them again. So, yeah. I don't know. Pacing is difficult. Let's turn the page, shall we? I wanted to do one of these problems because these ones are surprising. And I think unless you've seen the technique and practiced it, so there are some problems in the book, and I'm not going to point them out for you necessarily because I think that spoils the game. But there are some problems that are like this. And basically, I've got some like x on the outside and x on the inside. It's not x squared, right? It's x to the 1 in both places. So as usual, I'm going to try to let u be the thing on the inside. So I'm going to let u equals 5x plus 1. So then du is equal to 5 dx's. And it kind of looks like we didn't win, because I need to multiply by a 5 and a 1 over 5. And then I've got an x left over. And I'm kind of like, oh my god, I have x's and u's. Usually I would give up at this point. And I know I haven't done any examples where I do like a u and that doesn't work out. And I think that's okay. I can't do everything in these videos. So what I'm going to do is I'm going to take this right here and I'm going to solve for x, right? And then I'm going to substitute into this thing right here. So if I do that, then I would have u minus 1 equals 5x, or a fifth of u minus 1 equals x. And now I'm purely in terms of u. So the cool thing right here was to realize that, oh, I could still do something to get rid of this x and turn it into that. And again, you might be like, but it doesn't look any better, but it does. I assure you it does look better, because what I'm going to do next is distribute this across both of those. I'm going to keep changing pen colors, because why not? So that'll turn into, let's pull out that 1/5 on that again. So I have 1 over 25, integral of u minus 1 times u to the half. Du is 1/25. And the integral of u to the 3/2 minus u to the half du. And I can totally do this with the power rule. So 1/25 of I really like that 25. Okay. And then, like, depending on how ambitious you're feeling, we can distribute that over. I'll go ahead and do it. So we'll have 2 over 1/25 u to the 5 halves minus 2 over 75 u to the 3 halves plus c. And as a final step, we'll go ahead and put in what u was. U was 5 halves plus 1, or 5x plus 1. And there are various ways that I could continue to simplify this. If you look at the way that the book does this example, they stop here. But depending on how you feel about halves, I could make this be like root x, 2 root x over 1/25 times 5x plus 1 squared minus, no, I think, hang on. There we go, minus 2 over 75, 5x plus 1, plus some constant c. And I don't know whether you like that more or less. Simplification is always in the eye of the beholder. I don't know. So I'll probably stop there. Hey, we're cooking along pretty good here. Let's turn our attention to definite integration. I think you should start doing these problems after you're good at doing just regular integration by substitution, because this adds another layer of complication. So in definite integration with u-substitution, change the bounds of integration. I have a Lightboard video specifically on this topic, and I think you should check it out. If u prime is continuous, and if f is continuous on the range of u, then when I integrate this thing right here, this is just doing u-substitution, the bounds change from a and b to u of a and u of b. That's all it says. And I give a pretty good example of that in this video here. So I think we visited this problem early, and I think it's fine. I think the repetition is okay, so let's let that be u. So du is 3x squared dx. I need a 3 integral from 0 to 2 of root u du, but that was x's. And I think it's really important to mark those. So now I need to pass these bounds of integration through my transformation because I'm entirely in terms of u. Or when I do the so there are 2 different paths you can go down, right? So let me do this one way, and I'll show you that I think that the other way is simpler, and then I'll just do the other way from now on. So I'm going to go ahead and do this as I've got a third of u to the 3 halves, 2 thirds. I don't think I've done this one yet. It just feels really familiar. Evaluated, damn it, evaluated from x equals 2 to x equals 0. And it's really important that I have those x's because here I have u and here I have x. And x is not the same as u, right? 2/9 of x cubed plus 1 to the 3 halves, evaluated from 0 to 2. And now I feel like I don't have to write my x equals because now I'm back purely into x's. Equals 2/9 of, let's see here, 8 plus 1 to the 3 halves minus 0 plus 1 to the 3 halves. It's 2/9 of something minus 1, 9 to the 3 halves. That halves is square root. And then that's 27 equals 2/9 of 26 equals 52 over 9. And I don't remember whether 52 divides with a 3. And I don't care right now. I think it does. 13, 2, no, maybe it doesn't. I think I'm stopped. Okay, anyways. So if I do it this way here, where I keep my bounds in terms of x, I should get the exact same thing as if I transform my bounds. So I'm going to go back to this step right here. And I'm going to go, I think I'll write in purple. I haven't written in purple yet. So I'm going to have 2/9 of u to the 3 halves evaluated from, okay, so I'm going to replace those with u equals. So I'm going to utilize this right here, particularly that part right there. And I'm going to say, well, what's u of 0 and u of 2? Why 0 and 2? Because those are my bounds of integration. Because those are going to go here and here. U of 0 is 1. U of 2 is 9. It's possible that they end up out of order. So it's not guaranteed that this, after you go through u, it's not guaranteed that this is bigger than this. It's not guaranteed. So this is equal to 2/9 of 9 to the 3 halves minus 1 to the 3 halves equals 2/9 of 3 to the 3rd minus 1 is equal to 2/9 of 26, which is 52. I'm thinking faster than I'm writing. 52 over 9. And they're the same. And I think that this path is easier, so I prefer to change my bounds of integration. If you don't change your bounds of integration, it's a really easy mistake to make, to accidentally plug in 0 and 2, and then you would get nonsense. Not nonsense necessarily, but the wrong answer. You get a value that's incorrect. So I have 2 more examples, and I think we should go through them, and then that's it for this packet. And I have, like I said, I have lots of Lightboard videos on this, because I know that students tend to struggle on it, at least some. So let's do 2 more definite integrals. Just stay where I want you to, thank you. So let's do the integral from 0 to pi over 4 of tangent cubed of theta, secant squared of theta d theta. The kerning is really weird on that. I should fix that. Okay, so I'm hunting. Do I know anything that the derivative of is tangent cubed? No. I know some stuff that the derivative is secant tangent. Right? The derivative of secant is secant tangent. But I don't think that's enough to take up everything in here. I'll be left over with some tangent squareds. And so I don't think that u equals secant theta is the right thing to choose. Instead, I remember, because I paid attention in chapter 3, that d theta of tangent theta is equal to secant squared of theta. So I'm going to let u equals tangent of theta, which means that du is equal to secant squared of theta, d theta, secant squared of theta d theta. That part right there is going to be u cubed. So this turns into the integral of u cubed du. And now I need to put u of 0 and u of pi over 4 here. U of 0 is equal to tangent of 0. Why did I write a theta? Because it's like writing 0. Tangent of 0 is equal to 0. And tangent of pi over 4 is equal to 1. So this is the integral from 0 to 1 of u cubed du is equal to u to the 4th over 4 evaluated from 0 to 1, which is equal to a quarter. Yeah. I far prefer changing the bounds of integration because it means I don't have to back substitute for what u was, and I get to just work with these. Like, it just eliminates a whole bunch of work to do this transformation. So I suggest you just do it. One more problem. What's the area under the graph of some function in this thing? I would encourage you to take a look at this problem and the previous one in the book. They have some pretty nice graphs that I think help explain some things. I'm not going to replicate them here. All right, so what's the area under the graph? It's the same thing as asking, what's the integral from 1 to 3 of x over x squared plus 1 dx? Yeah, I don't need a question mark. Well, okay, so we're going to get a handle on this. I think we should let that be u, because I watched my Lightboard video on what u should be a lot, and I'm getting pretty familiar with it. Why did I write plus 1? So we're going to change the bounds of integration. U of 1 is equal to 2, and u of 3 is equal to 10. Yep, it's totally what it turns into. This is equal to half of the natural log of the absolute value of u, evaluated from u equals 2 to u equals 10. I have good alignment. Everything is in terms of u. Feeling pretty good. Half of natural log of 10 minus natural log of 2. And I'm done. And I'm done. Well, hey, that's it. I think that's the fastest I've ever covered substitution. I think all the necessary ingredients are there. If you have ongoing trouble with the problems, I would invite you to explicitly follow the steps that I suggest here. And if those don't work for you, then go ahead and check out my videos. I make these specifically so that people can watch them and use them when doing problems about this. So this lecture is not comprehensive. No lecture ever can be. There's plenty of other material in the book. I do believe I covered all of the major important stuff. Do lots of problems, get lots of practice, and I will look forward to rejoining you in our class discussion. Thank you so much, and I'll talk to you later. Bye.